Now we're going to look at Chapter 2, Section 2. Limits of a function and limit laws. Now, how this relates to what we just talked about. Well, in Section 1, we looked at the difference quotient. And when we first solved this, we got an equation. And so we said, as h goes to 0, the answer becomes whatever the x value is. And then the last part, the instantaneous, what we did there is we started getting closer and closer and closer to the points. In this section, we're going to talk about a concept called the limits. This is going to lead us to define the function called the derivative in calculus. And I apologize in advance because we're going to go through some very tedious, difficult parts in this section. But when we get to the next part, it's going to be super easy. What's going to take us half an hour to do here will take us 10 seconds later on. But we have to cover it to understand what's going on. All right, so in this one here, let's look at, we'll work at this example 1. How does the function f of x equals dy dx behave near x equals 1? Basically, we're saying here, as x approaches 1, f of x goes to what number? We'll call some. If you plugged in 1 in there, what happens? You get 0 over 0. You get undefined. You cannot divide by zeros. But before you do anything, whenever you talk about equations and it says at x equals 1, first thing you do is always just plug it in there, see what happens. If you plug it in there, what happens? We get what? We get 1 squared minus 1, 1 minus 1. We get 0 over 0. Whenever that happens, whenever you get 0 over 0, that's a very good sign. Because what does this tell us? It tells us that the numerator and the denominator have something in common. Since they have something in common, maybe that something can be removed. So if we have x squared minus 1 over x minus 1, the only thing we can do is we can factor out the top. It's the difference of 2 squares. X squared minus 1 squared. What's the formula for difference of 2 squares in factoring from algebra? X plus 1, x minus 1, right. Well, now we see that the x minus 1s cancel. So our function now becomes x plus 1. So this function, f of x, it behaves when as x nears 1, it equals 2. the function f of x, as x approaches 1, the function approaches the value 2. As x approaches 1, the function f of x approaches 2. No, it doesn't equal 2. It simply approaches 2. What does that mean? Think back in algebra. What does that mean? Graphically, what this would tell us is this. Our curve, no matter what the graph looks like, it will look like this. Remember, we said, what does the equation look like at x equals 1? But because we factor out the x minus 1 part, because we took care of that part, we're going to have a hole. It's no longer going to be discontinuous at 1. It means now at 1, we're going to have a hole. And the function will approach the value 2. So as we get closer to 1, these values will get us closer to the value of 2. As we approach 1 from this side, these values are going to get closer to 2. We'll never get to it because we can't. Because it's a hole. We canceled it out. This is how we're going to introduce the concept of limits. Limits are values, are numbers that the function doesn't have to actually get to. It simply has to approach. That's what a limit is. Let's look at the examples. So here's informal. An informal description of a limit of a function. Basically, it's this. As x approaches some value c, that function as, remember, this is a function f of x. When x approaches c, that function approaches some limit value. It's represented like this. It's red, the limit of f of x, the limit of f of x as x approaches c equals the limit value L. So as x approaches c, f of x approaches L. Some limit value. Here's example 1. They're just, you know. What's that? Question? When I let you all out. You're ready to go already? I mean, the door's always, again, there is no attendance here. You can leave anytime you want to. So, but we'll still go on. So for example, the example we had earlier,
Denominator and numerator are the same number, like zero.
if it's 0 over 0, only if it's 0 over 0. Right. So what this says is the limit as x approaches c of f of x equals L. So the way we'd write it for this function would be the limit as x approaches 1 of x squared minus 1 x minus 1 equals 2. Because the limit x plus 1 x minus 1 over x minus 1, these cancel, so we have the limit as x approaches 1 of x plus 1. That's what's happening. Again, this number 2 does not mean that that's what the value the function equals. It simply means that that's the value that the function is approaching as x gets closer to 1. Because remember, the graph will have a hole at that point 1, 2. That's what that means.
So we're always gonna have a point of which a point at which we're using. That'll tell us what point we're approaching.
Well, and sometimes you can get to it. For example, I can give you the equation limit as x approaches 2 of x squared. What's that going to equal? Just as x approaches 2, plug it in there. If it works, it's great. If it doesn't work, like this last one, if I plug in 1, I get 0 over 0. Then I got to do something else. But if it works, you're done. That's the value the function is going to, this is the function. As x approaches 2, it's going to equal 4. So that's the concept we have to, it's going to be very hard to understand is it doesn't have to exist to be a value. It just simply has to approach that value. For example, let's look at these. Here's the example of the first one we had, the x squared over minus 1. As x gets closer to 1, remember, it's a hole. Even though it's not defined at 1 because it's 0 over 0, 0 is on the bottom. The function itself does approach 2. Now, if we have a composite function, I mean, a piecewise defined function, at 1, we have to use this one. So when x is 1, the point is there. But the rest of this equation, the rest of this graph, from both directions, this is getting closer to 2, this is getting closer to 2. So the limit is 2. Even though it doesn't exist at 2, it's whatever it's approaching. And likewise at this one, just plug it in there, 1 plus 1 is 2, you're done. So that's what the hardest part of this part's going to be about. So let's look at example 3. We find the limits of the identity function and of a constant function as x approaches c. This is example 3. f of x equals x. So the limit as x approaches c of x, again, just plug it in there. It's c. Whatever your x approaches, plug it in there, and that's what the answer is going to be. If it's a constant function, the limit as x approaches c of the constant function is always going to be the constant function. What does the graph of this one look like? So if f of x equals 3, what does the graph look like? Yeah, it should be a horizontal line at 3, right, exactly. It'll be a horizontal line. So no matter what x I pick, as I get closer to it, it's always going to equal 3. So if you have a constant function, the limit will always be that constant function. If you have a linear function, then just plug it in there, see what happens. The only ones you have to worry about are quadratics or rational functions. Because when you do limits, which functions give you undefined answers, can give you possibly undefined answers? Which functions from the library of functions, which functions can give you undefined function solutions? Well, that depends if it's a function or not. I'm talking about, we know that rational functions, if f of x equals x plus 1 over x minus 3, I cannot use 3. So what I would do there, since I can't use, why can't I use 3? It'll make the bottom 0. So because this is a problem point, I would look at what happens as x gets closer to 3. As if you just plug it in there. But that's what we're talking about in this section is we have to look at all the points for x going to 3 from negative, let's say -4, -2, -1, 1, and then 4, 5, 6. Do they give you, do these values all approach a similar point? When it gets closer to 3, does it approach a value? Let me show you. No, you're thinking too much on there. Oop. So if you notice this example I gave you, what do we have? Whenever you have, if you put it inside 3 inside there, what's that called? It's a vertical asymptote. Vertical asymptote is where the function is undefined, where the rational function is undefined. There's the zeros on the bottom. So what happens to the curve as I approach that value from both sides? So here's 3 right there. What is it, as I come from it from the right, what happens to the graph? It goes to infinity. If I come from it from the left, what happens? It goes to negative infinity. So because they go to opposite directions, there's no limit. both sides have to approach the same value for it to be a limit. What's that? It's just for a general example. It's gonna be the same thing, because what you're looking at here is here you have a vertical asymptote at 3. So from the right-hand side, it's going to positive infinity. From the next side, left side, it's going to negative infinity. Only thing that the +1, -1, only thing that would do is really just adjust this a little bit vertically, and does nothing else for the vertical asymptote. But basically, what I'm looking at here is limits look at where does a function become undefined. That's the point we're interested in. I don't care about the rest of the points. The only point that's interest to me is at 3. What happens to the function as I go to 3? Because that's the only point that makes it of anything interest. If I said x equals 6, then I can just plug it in there. 6 + 1, 6 - 3, 7/3. And there's your limit.
So then how do you write that?
And that's what we'll get to. Because it said, if the limit doesn't exist, then it doesn't exist. There is no limit at that point. Because we're looking at something it's called divergent. It's going opposite from each other. What number was that one? 3? Let's look at example 4. Would you 3? Yeah. Example 4. Discuss the behavior of the following functions. Okay. U of x is equal to 0 and 1. When x is less than 0, when x is less than equal to 1. As x goes to 0. So as x goes to 0, what happens here? Let's look at the graph look like. When x is less than 0, the answer is 0. And when x is greater than equal to 1, the answer is 1. As x approaches 0, well, when it approaches 0, it's 0 from this side, but what is it from this side? If it's coming from this way, it's 1. If it's coming from this way, it's 0. Because they approach different values, there is no limit. It has to approach the same value from both directions. B, g of x. 1/x and 0. What happens there? Remember, we're looking at as x goes to 0. It doesn't have to exist at that point. For a limit to exist, it doesn't have to actually exist physically at that point. It simply has to approach from both sides. In other words, what I'm trying to get through there is this, is at 1, there is no point 1, 2, because it's all open circle there. but the limit is 2 as x approaches 1. Because as x approaches 1, these values are all getting closer, closer, closer to 2. These values are all getting closer, 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 closer to 2.
Was it up to including 2, or is it?
Not including, it just has to be up to. This has to approach that value. So likewise, now in this one, what does that graph look like? 1 over x. Yeah, you guys don't need a calculator. If it's positive, it looks like this. If it's negative, it looks like this. And at 0, it's 0. So as x approaches 0, what happens? This side goes to positive infinity. This side goes to negative infinity. So it goes opposite directions. There is no limit. And then the third one is f of x 0 sine 1 over x. Oop, x is less than 0. I should change that. And x is greater than 0. So less than equal to 0, it's 0. What about when it's greater than?
It's still 0, right?
Well, it's bounded by 1 negative 1. There's a sine function. It cannot be 0. So with this, the graph is going to be very, 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 very active first. And then it's going to dampen out. So as x gets bigger, this graph evens out. But at first, it's gonna be, the intervals are very, very small. So it has no limit. Because it, on the right-hand side, it goes from 1 to negative 1 to 0. And left-hand side is always 0. So there's no consistent point that it's approaching. It'll make more sense. The more we look at these things, the more we do these things, it'll make more sense. Limit laws. Okay, so we have the limit of f of x equals L as x approaches C, and the limit of g of x equals M when x goes to the same value C. The sum law, sum rule. The limit of f of x plus g of x as x approaches C. What happens here is it's the same as the limit of f of x plus the limit of g of x equals L plus M. The difference rule is the same as this one. F of x minus g of x equals L minus M. We expand it the same way. The constant multiple rule. So if I have the limit as x approaches C of some constant times function, If you have a constant, they come out in front of the limit. So the limit of f of x is L, so it's KL. Product rule. And the funny thing about it is a lot of these rules are going to be the same when we do with derivatives and integrals. We'll have the same, and they'll look the same. Instead of limits, you'll have derivatives. Instead of derivatives, you have integrals. But they all follow the same logic. So the limit, it is, that's it is, it is just that simple. F of x times g of x is the limit of f times the limit of g, which is L times m. Can you guess what the quotient rule is going to be? The limit of f over the limit of g will make it. Yep. What number was that one? Yep. The limit of f of x over g of x is L over m. Power rule is the limit of some function raised to a power is equal to that limit raised to the power. Whereas the exponent really doesn't accomplish much because it's inside the function. And same thing. But if you think about it, the power rule and the root rule are the same thing. Because the nth root of x is an exponent. So it really doesn't matter. Oop. All right, so let's do some examples here. How many do we have here? What time is it now? Oh, I thought it was 12. Okay, well, we'll call it a day there. I mean, it is, trust me, it is just that simple. Well, yes, I do apologize, everybody. I couldn't see, I thought I was looking at the because it looks like to me there's 4 arms in that thing from here because of the glare. So from now on, just throw something at me if I'm getting too late. So, okay, I should ask you guys, what time do you want to call it a day? Because